All right, now we're going to talk about something called one-to-one, which I hope you're familiar with from algebra, and onto. These two big ideas are used in the next subsection about isomorphisms. But before I start on all of that, I just want to apologize in advance. This video is particularly long. You might not need all of it, but right now it's kind of in its most raw state, if you will. But with that said, let's get started. At the beginning of this chapter, I talked about transformations as really being a more generalized case of functions. So before we start talking about one-to-one transformations or onto transformations, I want to talk about one-to-one functions. And hopefully that will be familiar to you. A function is, let's use f of x equals x squared. Now, there are several different ways to determine whether or not this is a function. The easiest, I think, and it speaks back to the definition of a function, but the easiest way I think to do this is to draw a graph of the function, or to draw a graph of the relation we're testing to see if it's a function, and then perform the vertical line test. The vertical line test helps us see that every x value that we might choose only has one y output, right? This is my x-axis here, and this is my y-axis, and y equals f of x. So y is equal to whatever you get when you plug x into the function. So for example, if this x here is 1, then when you square 1, you get 1. So the output y equals f of x is also 1. If x is 2, however, then the output is going to be 4, because 2 squared is 4. And I'm saying that in sort of terms of the function, but I'm showing it in terms of the graph of the function. The vertical line test helps us see that this is a function because every x only has one y associated with it. That's what it means to be a function. We can describe that using much more formal language if we want to or need to, but that's essentially what it means. Each input only has one output. An example of something that is not a function is, let's go with just the unit circle, x squared plus y squared equals 1. Okay, that's a very bad unit circle, but it'll do. When I draw a vertical line through there, I get not one, but two different y values for the same x value input, right? If x is 1, y is both whatever that y value is and whatever that y value is. Now you might be thinking, oh, but I can solve this for y. You can. I was in the wrong color, hang on. Let's see, if we subtract x squared from both sides, we get y squared equals 1 minus x squared. And then we take the square root of both sides, and we end up with y equals 1, the square root of 1 minus x squared, right? But not quite, because remember that when I take a square root, I have to consider the possibility that either a positive or negative number has been squared to give me that y squared value. So there are actually two parts to this. We have the positive square root of 1 minus x squared, and we have the negative square root of 1 minus x squared. So this is not a function because it fails the vertical line test, and it fails the vertical line test because even one x value has two different y value outputs. Now this one happens to have several, but that doesn't matter. As long as there's one, if there's even one would be a better way to say it, if there's even one place where the graph of the function fails the vertical line test, then the relation you're graphing is not a function. Now hopefully that's all pretty solid knowledge for us at this point. But we're going to use the same idea to discuss the idea of what it means to be one-to-one. If we can talk about functions as special cases of transformations, in other words, if we can think of transformations in a sense, as functions, then we can say that a transformation, wrong color again, a transformation is something that takes some input, we usually call those vectors, and does something to it. Let's see, how do I want to represent that here? Let's just say that it operates on the vector, and it only produces one output when it does so. Okay, so here's a function, here's a transformation. Now, back to our function, back to our y equals x squared function, f of x equals x squared. This function is not what we call a one-to-one function because it fails the horizontal line test. And here I'll remind you that what it means to be one-to-one is that for any particular y value, I can only trace back to one specific x value. And here I have two x values that when you plug them in, as it were, will spit out the same y value. Okay, so a relation is a function if for every x there is only one y. A function is one-to-one. First of all, it has to be a function, right? If it fails the vertical line test, then all bets are off. We can't do anything with it. But if it passes the vertical line test, then it's a function, and we can test to see if that function is one-to-one. A reminder, a relation is a function if each individual x only has one associated y value with it. A function is one-to-one if each individual y value only has one input x associated with it. So this one is not a one-to-one function. It's a function, but it's not one-to-one. What's an example of a function that is one-to-one? Y equals, I'll do g of x. G of x equals x cubed, for example. That graph looks something like this, depending on the scale on my axes. And that graph does pass the horizontal line test. Let me use the same colors I did for my x squared graph here. There we go. That graph has, for each y value, and you can test this all up and down the range, okay? Every single y only comes from one x. Unlike this one here, where every single y may have come from more than one x. This one is not one-to-one. This one is one-to-one. And that's the general idea of one-to-oneness. Let's take a little bit of a look at what the vocabulary that your book uses, the definition that your book uses. It says that a transformation from U to V, transformation T from U to V, is called one-to-one if the following statement is true. For every A and B and U, so for everything that's in the domain of the transformation, if for everything in there, transforming A and transforming B, if those are equal, in other words, if the output when you plug A in and the output when you plug B in, if those outputs are equal, then that means that the inputs also have to be equal. I could take this, the word transformation out here, and replace it with the word function. And I could take T mapping U onto V and replace it with f of x equals y, or let me use the same notation actually. F maps the domain onto the range. We say that that's one-to-one if for every x1 and x2 that lives in the domain then the outputs are equal f of x1 and f of x2 are equal, then x1 must have to equal x2. So let's see if we can go over this quickly and see what it means. A function f that maps D onto R, maps from the domain onto the range, is called one-to-one if this sentence is true. What does that sentence mean? Instead of for every, I could say for any two, or for anything that belongs, for every x1 and x2 that I pull from the domain, or that I might choose from the domain, for any possible two input values, the statement, there needs to be a comma here actually, it really does make a difference. The statement f of x1 equals f of x2 means, or must conclude, that x1 and x2 are the same. In other words, if the outputs are the same, then the inputs are the same. Okay, so how do we read this? A function is one-to-one if the following is true. Any two inputs, for any two inputs you choose, the outputs are equal means the inputs are equal. So I know I've gone over that several times, but it's pretty subtle. It's kind of hard to really land on and stick the landing, as it were. So that's what it means for a function to be one-to-one. But as you saw, I just erased the word transformation and replaced it with the word function. So I could go back and replace the word function with the word transformation, and I've got the definition of one-to-one for a transformation. So whether you're talking about a transformation or a function, I hope that this definition makes a little bit more sense now, because what I'm saying, if I go back to my graph, I'll use my x cubed graph because that one actually is one-to-one, whereas the x squared one is not. If I have two equal outputs, then my inputs must also be the same number. If the output is 1, I'm looking at this graph here, if the output is 1, then the input can only be positive 1. If the outputs are both negative 1, right, if I'm looking at this y value down here, negative 1, then my inputs, that can only be negative 1. It can't be anything else. So this statement is for every, this one right here. This is the condition that has to be met in order for this definition to hold. Okay, so that's what we mean by one-to-one. I'm going to come back and look at it in a little bit more of a general sense. We'll talk about transformations, one-to-oneness for transformations. But before I do that, I want to talk about onto, what it means to be onto in terms of the realm of functions as well. Because again, we're in a familiar environment here. And so if we can talk about it where it's familiar first, then it hopefully will make a little bit more sense in this newer environment called transformations. So I'm going to go to a new screen, but I'm going to be talking there about what it means to be onto in terms of functions. Okay, I'm starting with my definition this time. This is what it means for a function to be onto. And again, I'm dealing with functions at this point, not transformations in general. In the previous, on the previous screen, I circled this. This is a condition that has to be met. Every y in the range, and I've labeled this R range so we don't confuse this with the real numbers. Every y in the collection of outputs, right? That's what the range is. Every y in the collection of outputs, for every single one of them, there's at least one x in the domain so that the function maps x to y. Okay, so what does that really mean? Well, if it's a function, then whenever I grab an x, it's only going to go to one y. Now I'm kind of intentionally mixing up my subscripts here because there's no guarantee which one is going to map to which one, but the point is that x2 is only going to map to one of the possible outputs, right? One of the values in the range. That's what it means to be a function. If I drew another line from x2 to y2, then I would not have a function. Okay, so I'm going to get rid of that. Maybe not do quite as good a job as I'd like because I don't want to take too much time on it. If I took x1 and also mapped it to y1, would that still be a function? Well, sure, because for that x, it's only mapping to one y. It happens to be the same y, but that's okay. It's still a function. Is it a one-to-one function? Well, no, because now I have a y that maps back to two different x's. So this is not a one-to-one function. And the question now, of course, is it an onto function? Well, to be onto, I have to be able to pick any y and find at least one x in the domain so that that y comes from plugging that x into the function. So let's pick y1. If y1 has at least one x in the domain, I've selected my y, it's going to be y1. Does it have at least one x in the domain so that plugging that x into f gives me y1? Sure, in fact it has two, but it meets the criteria that there's at least one. Okay, now let's pick a different one. Does y3 have at least one x so that y3 comes from plugging some x into f? We haven't mapped all the possibilities yet, but the point here I want to make is that I have to be able to do that for every single y in the range. Right now, it looks like only one of the values in the range can be mapped back to something in the domain. So at the moment, it looks like this may not be onto. I want to also make sure that we understand that we're coming from the range, not the codomain. Okay, so remember that the codomain is the superset. The range is the list of all the possible outcomes, all the possible actual outputs of plugging things into this function. So there are things out here, for example, that I don't have to worry about. But within the range, within this circle here, if there's anything that doesn't map back to some x value, then this is not onto. Let's take a look at our function, f of x equals x squared again. I know it's a function because it passed the vertical line test, and that means that any x value only has one possible y output. Graphically, we can say that this is a function because for a particular x, there is only one y. This x does not also map to any other y at all. So this is definitely a function. This function is not a one-to-one function because if I pick any y, I may find that some map back to more than one x. So while it's a function, it's not a one-to-one function. The question is it an onto function? And to answer that question, we have to look at all the possible y values. So I'm going to highlight the y values here. And then we're going to say that everything on the positive y-axis, everything, forever, has a value so that if I pick one of those y values, I can find the x, or at least one x, that maps to it. And that's what it means to be onto. So by my definition of what the range is here, this is an onto function. If I define the range as all positive integers, then this is onto. If I define the range as the y-axis, including the negative y values, then it's not onto, because I have some values here that do not map back to anything in the domain. Right, let's look at the definition again. A function is onto if this statement is true. Let's check this statement for this function. Every y in R has at least one x so that f of x equals y. If this is my y, what is the x that maps to that? There isn't one. So this condition is not met, and so the function is not onto. So in part, it's going to be imperative that we check how we're defining our range, right? We have to know what the range is in order to determine whether a function is onto. Before I go on, I just want to make one other observation here, and that is that if I, for some reason, I have this tiny eraser, there it goes. If I redefine my domain again so that it is, sorry, my range again, so that it is, I'm going to say the range is the set of all positive real numbers and the number 0. Okay, if I define the range that way, then this function is onto, right? Everything in the range gets used up, essentially. It can be mapped back to at least one x, one thing in the domain. This function is onto, but it's not one-to-one. So it's possible to have a function that is onto that is not one-to-one. It's also possible to have a function that is one-to-one but not onto. It's possible that a function can be both one-to-one and onto, or that it can be neither. And so now I'm going to take another screen and take a look at the illustration that your textbook uses, which I think is really quite telling. Before I do that, just very quickly, note that what I'm saying here is that if I could list all the x's, right? If I could list all these x's, x1, x2, x3, there's an infinite number of them, but if I could list them, then I could map each one of those to some y value, right? And the question is, can I map all of them? Do they map to the entire, if I can map all of them, then I have a relation, is really all that means. If each one only goes to one y when I map them, then I have a function. If each y is only attached back to one x, then I have a one-to-one function. And if all of the y's get used up one way or another, then I have an onto function. Okay, so keep that in mind as I go to this next screen and bring in the diagram in your textbook. Okay, this is the diagram in your book. It's right under the subtitle, one-to-one and onto transformations. And we're going to start with the assumption that we're really just talking about functions here. And we'll come back. Remember that functions are just special cases of transformations. But that special case is where we're comfortable. We're quite familiar with those. And let's take a look at all of these. These are all functions, every single one of these. A function is just something that when you plug in an x, spits out a y, but it doesn't spit out more than one y. If I add a line, let's see, I'll get a red pen here. If I add a line like, for example, this, well, that's no longer a function because my x equals c spits out both y equals 1 and y equals 2. So now it's no longer a function. It's okay for two different x's to go to the same y, like this one right here. That's still a function. This just says this x goes to this y, and it doesn't go to any other y. This x goes to this y, and it does not go to any other y. So this is still a function, but it's not one-to-one, because for any given y, even if I only have one, if I can trace it back to more than one x, now it's not a one-to-one function, okay? It's also not onto because I haven't used up everything in the range. I don't have anything in my domain that maps to 4 in the range, so this is not a one-to-one function. It's a function, but it's not one-to-one. Sorry, it's not an onto function. It's not onto because I didn't use up the entire range, and it's not one-to-one because I have two things that I can map to one of the elements in the range. So this is neither one-to-one nor onto. This one is one-to-one but not onto. It's one-to-one because there are no duplicate y's here. See how there's a duplicate in the y column? There are no duplicates in the x column. That's how we decided this was not, that this was a function. If I had c going to 2, for example, now I have a duplicate. I have two things coming out of c, so it's not a function. Here I have two things going into 2, so it's not a one-to-one function. You see the difference? Okay, so this one is one-to-one because there is, for every c, for every x, there's exactly one y. That's what makes it a function. For every y, I can only trace back to one x, right? The fact that this is this y value doesn't trace back to anything is okay in terms of being one-to-one. Every value that I have in my range only maps back to one value in my domain. This one is onto but not one-to-one. It's not one-to-one because I can take this value here and trace it back to two different. This is like saying x equals 1. If my function is y equals x squared, then I can trace that back to both positive 1 and negative 1. So this is not one-to-one, but it is onto because I've used up everything in my range. And this one is both, right? I've used up my entire range, so it's onto, and there are no duplications in the y column. So it's also one-to-one. Okay, so one-to-one is not new vocabulary. Onto is new vocabulary, but we're not just interested in working with functions here. Functions are a special case of transformations. Functions take something in a collection we call a domain and do something to it so that they end up in another collection we call a range. Transformations do the same thing, but with functions, we're only ever taking things out of the domain that is the real numbers, and we're only ever mapping to the real numbers, sometimes the complex numbers. But with transformations, our domain could be the real numbers, but it could also be polynomials. And our domain might be different from our range. It might be that our domain is polynomials and our range is 2 by 2 matrices, for example. So we need to be able to take what we've learned here about one-to-one and onto and translate it so that we're talking about it in terms not just of functions, but of all possible transformations. So let's take a look at a couple of examples. Okay, for our first example, we're going to look at a transformation t of x. The transformation of a vector x is equal to a matrix times the input vector. And the matrix we're going to use is A, which is 1, 0, 0, 1, 1, 0. There's a duplicate line here, so we know we can reduce this to something other than this. And we're given the transformation, but we're also told that the transformation takes things in R2 and puts them into R3. So without seeing an example of what an input looks like, I know that I can come up with one because they're all in R2. This is my domain and this is my range. So let's find to start with, let's take something in, let's let x1 be 2, negative 3. And this is something that's in my domain. It's a vector in R2, and I'm going to apply the transformation to it. So the transformation of 2, negative 3 is equal to A, which is 1, 0, 0, 1, 1, 0, times the vector 2, negative 3, and that gives me, and I'm going into R3, so my result should be a vector in R3. That should be obvious because this is a 3 by 1 matrix, sorry, a 3 by 2 matrix. This is a 2 by 1 matrix, so I can do the multiplication and the result will be a 3 by 1 vector. So what is that result? I'm going to have 1 times 2 plus 0 times negative 3, 0 times 2 plus negative 1 times negative 3, and 1 times 2 plus 0 times negative 3. So that's the result of that particular vector input. That gives me that particular vector output. Now I've done this example just because I wanted to see what this transformation does. When I take something from here and do this transformation to it, what does it end up looking like? I don't, strictly speaking, need to do this in order to answer the question, is T 1 to 1? But I've done it sort of just to clarify the situation that we find ourselves in. Any vector in R2, we know, is going to look like this. I think I'll use AB. It's a little easier than x1, x2. And the transformation then of that vector is going to be, let me get rid of this. The transformation is going to be the matrix 1, 0, 0, 1, 1, 0 times AB. And I'm going to get then 1 times A plus 0 times B, 0 times A plus 1 times B, and 1 times A plus 0 times B. And you can see the pattern here, right? This is with general numbers, this is with specific numbers, but you're always going to get, in this transformation, a 3 by 1 matrix, which is made up of the first two components from the input vector plus the third component, which is the first component repeated. Right? That's always going to happen. Now the question we're asked here is this transformation 1 to 1? In order to determine that, we need to find out whether, or we need to examine whether there are outputs. We would call these our y values if we were working with a function, but they're just outputs. If there are outputs that map back to more than one different input. Remember that f of x equals x squared is not 1 to 1, because if the output is 1, the input could be either 1 or negative 1. Either 1 or negative 1 when you square it gives you 1. So does the output here, does any output map back possibly to more than one possible input? And the answer is no. So this transformation is 1 to 1. Let's take a look at the more formal definition, though. Remember that to be 1 to 1, this has to be true about a transformation. If two outputs are the same, then the two inputs must also have been equal. It's important to notice the order this statement is made. If the outputs are the same, then the inputs must be the same. So I have to start with two outputs. Let's take T of AB, AB, and say that it's equal to T of CD. If that's true, we know what the output here is. It's going to be ABA, because that's what this particular transformation does. And that means that the output here is going to be equal to CDC, because that's what the transformation does. But if that's the case, then since vectors are only equal if they're equal component-wise, then A must be equal to C, B must be equal to D. So the vector AB must be equal to the vector CD. So what I've said here is that if my two outputs are the same, then they look like this, so my inputs must also be equal. So this is the formal way to show that a transformation is 1 to 1. Now we need to look at what it means for a transformation to be onto. So I'll do that on the next screen. All right, we have a very similar transformation here. It's mapping a vector onto a matrix vector product. But this time we're going from R3 to R2, and our matrix is a little different. Instead of a 3 by 2, we have a 2 by 3. So to start with, I'll do the same thing as I did before. T of x is equal to A times x, and that is equal to A, which is the matrix 1, 1, 0, 0, 1, 1, times the vector x. And x can be anything in R3, anything that comes from R3. So this time I'm going to go straight for a more generic example, and I'll call it A, B, C. A, B, and C are implied there to be real numbers because this is a real number valued vector. All right, this multiplication is going to give me 2 by 1 vector. What does that look like? Well, in this case, it's going to be 1 times A plus 1 times B plus 0 times C for my first component. So 1 times A plus 1 times B. And my second component will look like this: 0 times A plus 1 times B plus 1 times C. So B plus C. So all of my outputs look like that. Now let's remember that this notation tells us that the transformation takes things in R3 and puts them in R2. And R3 is the domain, and R2 is the codomain. So if everything in the codomain gets used up, then the transformation will be onto. But another way to say that is that if everything in the codomain gets used up, then the codomain equals the range, right? Because the range is the actual outputs, and the codomain is just the possible outputs. So if the range and the codomain are the same, then the transformation is onto. It's just another way to say what it means to be onto. So how do we check that? Well, once again, we're going to start with something in the codomain. We're going to pick something random from the codomain. And we're going to show that no matter what our choice is, it has to map back to the domain. It has to come from having plugged in something from the domain. Now, if the codomain is guaranteed to have something from the domain, right, maps back to something from the domain, then the codomain is the range, because the codomain is made up of all the actual outcomes, all the actual outputs. So the codomain and the range are equal, and that's what it means to be one-to-one. So we're going to check something from the codomain. And the way that we're going to check it is to say, well, to ask really, is there something in the domain that will produce this particular output, this generic output? If such an X exists, then it needs to be true that the transformation of that X produces that output. Let's try to take a slightly different approach with this one. Let's say that we have some X in R3, that's our domain, and we'll call our output vector Y, but we know that that's in R2. Then what we need to show here is that for any Y, any vector Y, there exists, or there is, a corresponding X. Having trouble writing for some reason. A corresponding vector X. So what does a Y look like? Let Y be the vector, let's go PQ. Okay, we know it's going to be an R2 vector because we're told that that's what our codomain is, and actually we worked out here that we have two rows. When you add these two real numbers together, you get a single real number. So you have two real number components here. This is what an output vector looks like that in that codomain. And what we want is, I'll write it that way, what we want is for the transformation of some X to be equal to Y. In other words, we want this thing here to have at least one solution. Well, what's another way to write this? We've got T of X is equal to A plus B, B plus C. That's what our T of X looks like for a random vector X. We let this equal X, right? This is my A, this is my X, and this is effectively my Y. I'm using Y here again because I'm sort of resorting to kind of function language just because I know it's a little bit more familiar. I want to show that the transformation on an X, which I know looks like this, can equal some PQ for any PQ. So I'm picking any random PQ. I'm picking any random Y in the codomain. I'm calling it PQ. And I want to show that the transformation of any random X can be made to look like that PQ. And in this case, what that tells me is that, I'll do it as an implies, that equality implies that A plus B equals P, and B plus C equals Q. But A, B, P, and B and C and Q, these are all real numbers, right? Every single one of these is a real number because they're coming from real number valued vectors. So A and B are real numbers, B and C are real numbers, P and Q are real numbers. Can I find two real numbers that add up to some real number P for any P? Sure. I don't care what P is, I can find a way to add up two numbers to get P. Now, there are actually lots of different ways, but that's okay as long as I can find one. And I would make the same argument for Q. I can find two numbers, any two real numbers, that add up to Q. And as long as I can find one, then I know that there is an A plus B combo that will give me P and a B plus C combo that will give me Q. Of course, the B's have to be the same in this particular case, right? But I can find that combination. And so this PQ thing has an answer, as it were. It has a solution. So to finish out this argument, I'm actually using logic rather than sort of mathematical symbolic notation. So I'll just say down here in the corner, since a vector PQ will always have I'll come back to that in a second, in R3, PQ in R2, the transformation T, I think I'll just call it T, is onto. Now I left this word out because I want to come back to it. There's an answer, there's a solution, but what do we call that? Way back at the very beginning of, when was that? Was it actually chapter 1? Be chapter 2, I don't remember. It was a long time ago. We talked about lots of different vocabulary around the domain and the range and the codomain. And in addition to those three words, we said that if you take an X and you map it to a Y, right? If you take an X from the domain and you map it to a Y in the range, then we say that that Y is the image of that X. We also said that the X was the preimage of the Y. So this is another way to discuss onto-ness. If something in the codomain always has a preimage, some preimage in the domain, then your transformation is onto. And rather than use a lot of symbolic notation here, I've used a little bit of that and then a logical argument. This is not a proof. It's just a demonstration that the particular individual transformation that I was given is onto this particular topic. If we have a transformation like the ones we've just been playing with, and I've labeled this as your book has done, T sub A, to suggest that the transformation is one where the operation on the vector is by left multiplication of a matrix, and that the matrix A is really going to be key to what we're going to talk about next. And that is that a transformation is going to turn out to be one-to-one if the columns of A are linearly independent. So if the columns of A are linearly independent. So if I take the A that I was working with in my first example, I had 1, 0, 0, 1, 1, 0. And I reduce that. I get 1, 0, 0, 1, 0, 0. I hope that's obvious because this is a scalar multiple of this one. So I just take negative this row and add it to this row and I get all zeros. And then I can look at the pivots. And the pivots in this new matrix are here. And that shows me, because there's zeros below them, those two columns are linearly independent. And therefore, the transformation T, therefore, T that took X and multiplied it by that matrix is 1 to 1. So all that work that we did to establish, proving that or demonstrating formally that a transformation was 1 to 1 is kind of moot because it turns out that this is a nice little shortcut. That said, it will stand many of you in good stead to have seen that more formal description of how to determine whether a transformation is 1 to 1. Now, A2 was 1, 1, 0, 0, 1, 1. And if I reduce that, I get 1, 0, negative 1, 0, 1, 1. Looking at those pivots, I can see I have two pivots there, but I can also see that I have a third column that can be written as a linear combination of the other two columns. That third column is not linearly independent. This was the matrix from my second example, so this was actually the matrix from my onto example, but I wanted to show you that this is a really quick and dirty way to show that that transformation was not onto, or sorry, is not 1 to 1. So I would say here that the transformation of a vector x by this transformation, by this matrix multiplication, is not 1 to 1. Okay? Now, that's for 1 to 1, but there's also a test for onto. And that is that if the columns of A, columns of my matrix A, span the codomain, then the transformation is onto. So let's check that. Do the columns of A span Rm? Well, in this case, we had a transformation T that went from R2 to R3. And in this case, we had a transformation T, I'll call this one T1 and this one T2, that went from R3 to R2. Okay, it's important. Here's my matrix A for the first transformation. Here's what I get when I row reduce it. Because those columns are linearly independent, I can look at that and say it's 1 to 1. But do the columns of A span R3? Well, they can't because there are only two of them. So this is 1 to 1, but not onto. Okay, that's our first transformation. For our second transformation, we've already established that it's not 1 to 1 because the columns are not linearly independent. But do those columns span R2? Well, we have two linearly independent columns, so yes, they do. So while it's not 1 to 1, it is onto. I should say T is not 1 to 1. T is 1 to 1, but not onto. So all of that, and I'm giving you this shortcut primarily because it's in your book anyway. This is theorem 6.3.1, 1 to 1 and onto transformations and the standard matrix. So that pretty much covers it for one-to-one and onto those big ideas. And our next video is going to take a look at how these are used in the description of something we called an isomorphism.